In our last video, we looked at the simple designs of beam and arch bridges. Now let's move into the modern age with the truss bridge. Truss bridges make use of a large frame called a truss that sits on top or below the bridge deck. In this case, it is on top. While it may seem like we are only adding weight to the deck, the design of the truss distributes the load through the frame so that the deck does not experience as much of a load. Each segment of the truss experiences different loads of either tension or compression. We apply 2 equal loads to the deck and calculate the loads in each segment, which are shown as percentages of the total load. You can see that the largest loads are on the end and top segments, while the middle segments have none. Remember that when we do the compression test. Spoiler alert! Let's see if this convict gets shot out of his truss jail. So how do you think the truss will break? Discuss. Thanks for coming, Yoda. I love your work. As you can see, the outer segments of the truss are the first to break because they were handling the largest part of the load. The diagram showed that the outer and top segments had the same loads. Why didn't the top break? That's because the top pieces are aligned along the grain of the wood, and wood is stronger in that direction. Adding the truss allowed the same deck length to hold 32 pounds, which is 25% stronger than the beam bridge of the same length. The final type of bridge we'll discuss is the iconic suspension bridge. Although the only suspension bridge around us is less than iconic, but the same principles apply. Suspension bridges utilize thick steel cables that support the deck and transfer the load to the towers and to the anchors at the end of the bridge. Supporting cables are used to suspend the bridge deck from the main cables. The main cables and supporting cables of the bridge are always under tension. The cables transfer the load to the towers, which experience compression, and also to the anchors at the end of the bridge. In our model, we used wires for the main cables and supporting cables. Some of the construction is not ideal because it is difficult to simulate some of the joining points and anchors on a small scale. For this test, we need a full cast of characters. The Misfits versus the Bike Gang. Oh, there's Crazy Guy again. Classic Crazy Guy. As force is applied, the cables transfer the load out to the towers and anchor points at the end. This force distribution maintains the integrity of the deck so that even when it does break, it doesn't really launch anyone. Unfortunately, I really want to see the Crazy Guy get launched. This bridge supported 32 pounds, which is the same as the truss bridge. The truss and suspension bridges were stronger than the long beam bridge, but weaker than the arch bridge. This may have been unexpected, but the real advantage of truss and suspension bridges are that they can span longer distances than beam and arch bridges. Now what we've all been waiting for. Crushing a Lego man.